Welcome back to the Lowdown on Physics. This is screencast number 11 in a series looking at VCE Unit 3 motion for physics, and today we will be looking at gravitational fields. Before we go any further, let's just recall what a field is. And a field is a region where an object will experience a force. So examples would include electric fields, magnetic fields, and of course gravitational fields. Now recall from Newton's universal law of gravitation that a gravitational field is a force of attraction between two objects. When we look at Earth and its gravitational field, it's a force of attraction always directed towards the center of the Earth. So at every space, wherever you are on the Earth, it's always down towards the center of the Earth. Notice that these lines are not equally spaced. They're closer at the surface of the Earth than they are further away. And what that means is that it's not a uniform field. So it will be stronger where the lines are closer, weaker where the lines are further apart. So what do gravitational forces cause? Gravitational forces cause weight. Weight is dependent on the mass. So we've got weight for an apple, we've got weight of a piano is greater, weight of a tank even greater. So it depends on the mass of the object as to the weight or the gravitational force that it will experience. Now Newton's law of gravitation tells us that strength is going to be proportional to the distance. In a space like within our classroom, it's going to be pretty uniform wherever we test it. But as we get further away, then it's going to drop dramatically. This is what we were just looking at in that diagram of the Earth and how the field lines spread out. So if we go to an altitude of 1,000 kilometers above the Earth, it drops to 7.3 meters per second squared, where normally it would be 9.8 meters per second squared at the surface on average. At an altitude of 5,000, so 5 times that, it drops to 3.1. Very, very weak gravitational field. So as I just mentioned, 9.8 meters per second squared at the surface of the Earth. That's a fairly average value. In fact, it's actually more like about 9.83, closer to the poles. Further away, it's actually, towards the equator, it's about 9.78 meters per second. And this is because the Earth's not actually perfectly spherical. If it was perfectly spherical, it would be equal all the way around, as long as the mass was constant all the way around. But in fact, the spinning effect probably makes it slightly wider at the equator, and therefore you're further from the center, and as a result, averaging about 9.78 meters per second squared. That's just for a bit of trivia for you. If we want to calculate the gravitational field strength, we use the equation G equals gm over r squared. How do we come to that? Well, we've got mg equals your force, which is gm over r squared. Divide by m, we lose the m off each side. And so the result is G equals gm over r squared. It's independent of the mass that's attracted to it. So it's independent of your mass, or the mass of the car, or the mass of the plane. G depends on the mass of the Earth and how far you are from the center of the Earth. So let's have a look at a couple of examples. Calculate the field strength, gravitational field strength, of the surface of the Moon. So we've got the mass of the Moon, we've got the radius, so we use G equals gm over r squared. Substituting in, G is our gravitational constant. Substitute in our mass, over r, don't forget to square it, that's a common mistake that people make. And we get 1.67 newtons per kilogram, about 1/6 that of the Earth, so we're spot on the money. Okay, second example, we've got a 50 kilogram piece of garbage. It's at a height of 1,000 kilometers above the Earth's surface. We're given the mass of the Earth and the radius of the Earth. Determine the gravitational field strength at this height. So here we've got G equal to 6.67 times 10 to the negative 11 times the mass of the Earth 6 times 10 to the 24, over 7.4 times 10 to the 6 squared. We've got 1,000 kilometres, which is 1 times 10 to the 6 metres. So we've got to add that to the radius to get 7.4, square that, and we've got 7.31 newtons per kilogram. That's it for finding gravitational field strength. It's just an extension of Newton's law of gravitation. So I'll see you in class shortly.